Okay, so this is a calculus video. It's my third video on integration by parts, following James Stewart's 6th edition of calculus. So this video starts off nice, right? Starts off easy enough. How does it work with definite integrals? So the initial video I did on integration by parts did indefinite integrals. Again, didn't have the A's and the B's. That's the difference between indefinite and definite. The definite goes from a particular point to a different particular point. So if you were taking the area under a curve, it would be from the curve at this point to the curve at this point. Anyway, definite integral, you know that, right? How does it work for integration by parts with a definite integral? Well, it's the same thing. The integral from a to b of u dv equals uv from a to b minus the integral of v du from a to b. And so I'm sorry, I haven't figured out how to get the bracket to go taller. Anyway, I will eventually, probably, long after, it's useful. Anyway, so let's go ahead. This is fine. This looks easy enough, right? But I decided to add on this example from the textbook. This is quite an example. It stretched my muscles. I'm going to be sore in the morning because there's a number of little things that this reviews. It's a great exercise. And so, although get ready, it's going to be painful. But this is a really good example because it reviews a lot of little unexpected twists. All right, let's dive right in. So if we're going to use integration by parts, we need to pick, well, we really only have two things here, right? We've got the inverse tangent of x and we've got dx. So I'm going to pick, remember, the integral of u dv equals uv minus the integral of v du. So I'm going to pick a dv that I can integrate well, and dx is my best candidate, right? So I'm going to let u, remember the integral of u dv, I'm going to let u equal the tangent of inverse tangent of x, and I'm going to let dv equal dx, right? Okay, so u is going to be the integral of u dv, u is going to be inverse tangent of x, and dv is going to be dx. Now, one thing that Stewart does in these examples that I think is helpful is he goes ahead and he finds what du is, and he goes ahead and he finds out what v is. So what is the derivative of the inverse tangent of x? I should have probably have a dx over here, just for righteousness sake. Hold on a second. Now mathematicians all around the world feel much better about me. So again, this is just something that we should have memorized. I'll be honest, I haven't memorized it. But the derivative of the inverse tangent is 1 over 1 plus x squared dx. All right, and so I picked dx as dv. That's easy because that means that v equals x. Wonderful. So now let's go ahead and integrate by parts. So the integral of u dv integral, this is u dv, is going to equal uv. So u is inverse tangent of x, there it is, times v, which is x, from 0 to 1, all right? We'll come back to that in a second, minus the integral from 0 to 1 of v du. Well, v is x, and du is that. All right, so far so good. This one we will vanquish. Let's go ahead and vanquish the first part. Let's go ahead and vanquish fairly easily. All right, so we're going to vanquish this part, and then we're going to vanquish this part. Let me go ahead and make one quick edit. Okay, now it's going to unfold little by little. All right, so let's go ahead and evaluate this. What is the inverse tangent of x times x from 0 to 1? Well, we're gonna plug in the 1, and then we're gonna subtract, plugging in the 0. So if we plug in the 1, the inverse tangent of 1 times 1, okay, minus, then we're going to plug in the 0, the inverse tangent of 0 times 0. Well, this is going to just disappear, bloop, bloop. And so what is the inverse tangent of 1? Okay, well, the inverse tangent of 1 is going to be, so the tangent, if you take the unit circle, the tangent is the sine over the cosine. So where on the unit circle is the sine over the cosine 1? Well, it's at 45 degrees, or pi over 4. Pi over 4 is where the tangent is 1. So if I want to know what the inverse tangent of 1 is, it's at pi over 4. So the inverse tangent of 1 is pi over 4. That's where the tangent is 1, right? If the tangent of pi over 4 is 1, then the inverse tangent of 1 is pi over 4. Okay, so there's the first muscle. Oh, my arm's going to be sore. You're making me do trig. I thought this was calculus. Anyway, so that's pi over 4. So now I've got my first part, right? I'm breaking it down, solving for this, and I know what this is. This is pi over 4. All right, so I've got the 1 down, 1 to go. How am I going to find out what the integral of this second part is? Well, I'm glad you asked. Let's go ahead. Let's use substitution. See, this is a double whammy. We're not only getting integration by parts, but we're getting substitution as well. All right, so let's go ahead and remember, what are we doing again? What are we doing? Where am I? Who am I? We're trying to use substitution to get the integral of this, right? X over 1 plus x squared dx, all right? So what I'm going to do is I'm going to let u equal that denominator, 1 plus x squared. That means that du is going to be the derivative of that, 2x dx, okay? And then I also need to figure out, so I've got this problem. I'm going to make this into u, and so I know that du is 2x dx, right? But I've got to change the scope of where it goes from what to what, from x's to u's. So when from 0 to 1, when x is let's go ahead back to my chart. It's from 0 to 1, right? From x equals 0 to x equals 1. So when x equals 0, u is going to equal 1, right? Because that'll disappear, whomp, whomp, and we'll be left with 1. And when x equals 1, then this is 1 squared, which is 1, plus 1 is 2. So when x equals 0, u will equal 1. And when x equals 1, u will equal 2. Okay, now we're ready. That means that the integral, which I'm trying to find here, this is what I'm trying to find, is going to equal, now see how I've replaced the numbers? It was from 0 to 1 when it was in x's. Now it's going to be from 1 to 2 when it's in u's. And then this is going to become du over 2u. How did that happen? Well, I set this equal to u, so the bottom becomes u. That's where that u comes from. And then du is going to be 2x dx. So I'm going to, how do I get rid of that 2? Well, if I take half, if I divide by 2, then the 2 and the divided by 2 cancels out. And so it keeps unity in the force. So, and that sucks up the dx as well. So the integral from 1 to 2 du over 2u is going to be the same as this. I've now substituted a u into the, I've taken 1 plus x squared, substituted u, and I've converted this equation to du over 2u. All right, now it's in a form that I can do, because I know that the integral of du over u is the natural logarithm of u, or at least the natural logarithm of the absolute value of u. So the 2 comes out as 1/2, that's fine. And now I go from the natural logarithm of u from 1 to 2. Okay, so let's break that down here. So the 1/2, the natural logarithm of u from 1 to 2, substitute in the 2, 1/2 times the natural logarithm of 2 minus natural logarithm of 1. Well, natural logarithm of 1, here's another muscle. Oh, this one's going to be sore. You know, if you look at the natural logarithm, the graph of the natural logarithm, it crosses the x-axis at 1. So when you take the natural logarithm of 1, it's 0. That's when it crosses the x-axis. And so this is going to disappear, and we're left with 1/2 the natural logarithm of 2. Shoo, both you're asking me to do trig and natural logarithms and substitution. What's next? Well, now we get to, now it's all done. It's pretty much over. We're going to put it all together now. This was the monstrosity that we were trying to simplify. We already did this, right? That equals pi over 4, and we now know that the second part equals, the second part equals 1/2 the natural log of 2. And so there you have it. That monstrosity, the integral from 0 to 1 of the inverse tangent x dx is going to equal pi over 4 minus the natural log of 2 over 3. I mean, over 2. Well, whew, I'm tired. I think I'm going to go take a nap. This has been another example of integration by parts.